Okay, so let's identify. Now that we've identified that the first order DE for number 1 is it is linear in Y. That's one useful thing to know. However, according to the instructions, you have to solve this using the homogeneous method. So we did try to test if the DE was homogeneous also, and it turns out that it is. We can say that the differential equation isn't homogeneous if, for example, this one is t squared and this one is just t. So they have actually, I'm not sure yet, just yet. But essentially, that is the idea. Yes. So you know that a certain expression isn't homogeneous if for example, it's easier to explain it using an example, e raised to x. So by policy, this is what we have to do. So we substitute. X becomes tx. So after that, we don't do anything else. And if we cannot remove the t or like segregate it, just like how we segregated here. So as you can see, although we substituted x as tx and y as ty, when we factor or like segregate t away, we still retain the original differential equation. So that is the main factor to determine if ADE is homogeneous. Okay, so this one is not homogeneous. After testing for homogeneity, we now proceed to so there's this policy. We still follow this default equation. So mdx plus ndy equal to 0. This comes from exact method. So the idea is you want to identify whether m or n is simpler. So this is m right now, it's x minus y. N is x. Okay, so we know that right now n is simpler. So what do we do? By policy, if n is simpler, we are going to use y equal to ux. Okay, if ever it were the other way around, m is simpler, then we use x equal to vy. Okay, so we'll use that later. Right now it's just n, so we can also manipulate this equation such that we're solving for u. That's going to be useful later. It's actually essential. And then you find the derivative of y equal to ux. Not quotient rule, product rule. So u dx plus x du. So we are going to use these in what will happen next, which is the substitution process. So again, this is the original differential equation, right? So substitute y as ux and dy as this one. Okay, so x minus our y, that is going to be ux, and then just copy dx plus x, just copy x, and then dy is this. u dx plus x du equal to 0. Okay, then let's simplify. X dx minus ux dx plus ux dx plus x squared du equal to 0. So I think we can cancel something, this and this. What we have left is x dx plus x squared du equal to 0. I think at this point, this is only the time when we start to uh, identify. Actually, yes. Usually at this point, the differential equation we have is variable separable. So let's try dividing everything by x squared. So we have x over, dx over x, and then du. I think this is sufficient enough. We can transpose du to the other side. Then we start to integrate. And in order to identify the general solution, we solve for, in this case, although not necessarily that you have to solve for x or y, or, well, yes, either the both of them. Usually this is already accepted, but we want to simplify it further. So we want to eliminate the ln, right? So put e on both sides, so e and ln cancel. What we have in the left side is just x. At the right side, we have u plus c, or yeah, e raised to c. I think that's it for this question. Let me just verify if the answer is correct. So, like I said, usually, let me just make a distinction. No? Usually, this is already accepted as the general solution. You only have a general solution. Oh, wait. Sorry. I almost forgot this. So we got this right, coming from y equal to ux. So we actually have to substitute. You're not supposed to forget that. So recall, u is equal to y over x. So substitute ln x equal to y over x plus c. Okay? So, wait a minute. Don't forget the minus sign. Okay? So, you can bring y over x to the left side. Although I don't think it really matters at this point. The answer is roughly the same anyways. So, yeah, either way is okay. If you have a condition, for example, given that y of 1 is equal to 0, so that gives you the idea that you can also find the constant, and basically the general solution with a constant value, like an actual value, just not writing c, that basically constitutes a particular solution. So do we have that kind of question? Actually, we do. Let's actually do that later. Let's proceed already to the next question. We are on a time limit. Okay. All that for just one question. Number 2. So, this is not variable separable. Can you check if it's exact? One. It is. I think it is exact. Okay, so yes, it is exact. Let's test for linearity. At this point, we can already solve. We already know one way of solving this differential equation. However, for practice purposes, let's see if it can be solved also by linear. Aside from what we already assume, that this is technically solvable by homogeneous. So test for linearity, x dy, x plus y. What if we transpose? Is it the same question as earlier? The only difference is a plus sign. That feels weird. So it's not linear in x. I think it's still linear in y, the same thing. Homogeneity, let's try to test it anyways. So tx replaces x, ty replaces y. Yep, homogeneous of degree 1. So let's identify now whether m or n is simpler. So obviously n is simpler. So what do we use? X equal to, y equal to ux. Okay. And again, u is equal to y over x. And find the derivative. dy is equal to u dx plus x du. Okay. Now we start to substitute. Original dE x plus ux dx plus x dy equal to 0. Okay. So simplify. So we can group these together. They all have dx. These are like terms, so we write 2ux. And that's it. And then dx. Other side, negative x squared du. Okay. Now, let's determine if it's variable separable. Let's try to factor out x. simplify. 1 plus 2u dx equal to negative x du. Okay, I think this is variable separable, no? Divide both sides by m and n. So negative dx over x equal to du over 1 plus 2u. And then, okay, we're good already. Now we integrate. Negative ln x equal to, let's try u, 1 plus 2u du, therefore is equal to 2 du. Okay, yes, it fits. Ln 1 over 2 u plus c. Okay, and then we can rewrite this as ln quantity 1 plus 2u raised to 1 half plus c. And then I think at this point it's okay. But wait, u is equal to y over x, right? So 2y over x raised to 1 half. I think this is good already. Let's see. Yeah, Gemini has a similar answer. Only that it's articulated in such a way that, okay, so let's eliminate the natural log. Actually, before that, negative ln x could be rewritten as ln x raised to negative 1. Okay, let's be clear on that. So x raised to negative 1 equal to 1 plus 2y over x raised to 1 half, and then plus e raised to c. What if we square both sides? So x raised to negative 2 equal to, okay, and then Ah, okay, hang on. What if we compile? What do I mean by that? Ah, no, it's just gonna complicate things further. I think this will suffice already. I'll just have to confirm this to my prof. But essentially, we followed all the necessary rules. Okay. Let's answer number 3. So x dx. So this is not variable separable for sure. At least not for now. You know what? Let's not test on each practice question anymore. Let's just get straight to the point. These are all homogeneous anyways, and we already mastered how to prove it. Or either that or it's easy. You just again substitute. Let x equal to tx, y equal to ty. Okay? So now, let's get straight to the point. Which is simpler, m or n? This is m. This is n. Again, following the formula m dx plus n dy equal to 0. You cannot interchange them. Okay? Therefore, it is wrong if it were to be like this. Okay? That's just gonna mess up your memory. You remember it exactly like this. Okay? So m is equal to x. Oh, m is simpler. So what do we use? If n were simpler, we'd use y equal to ux. But now that it's m, we use x equal to vy, xy. Okay? Therefore, we can also say that v is equal to x over y. We're gonna use this later, after integration, so that we would be able to finalize our general solution. So right now, now that we have x equal to vy, you derive. So dx is equal to v dy plus y dv. Okay? Again, you need these two for the substitution part of the solution. So looking here, x is vy, and then copy, no, not copy. Dx actually has a different, you just copy, no? Substitute. And then y minus 2x, x is vy. And then dy copy only, then equal to 0. Simplify. V squared y dy plus vy squared dv plus y dy minus 2vy dy equal to 0. So looking, we cannot simplify anything yet. V squared y plus y minus 2vy. Okay, so we're done segregating. So what do we do next? After substitution, you might think that we could already start integration, but it's actually, it might mess up the solution because we still have to do something before that. Um, let's try to factor y here. So v squared plus 1 minus 2v. Now we're getting somewhere. Minus 2v plus 1. Let's arrange it that way. And then vy squared dv equal to 0. Is this variable separable? Yes, I think it is variable separable. We have y and v in a dy, also y and v in a dv. So that's a positive sign. It's actually pretty obvious. There are some instances where the dE being variable separable isn't so obvious. So you still have to scrutinize, no? So yeah, it just takes a lot of practice where I'm seeing it. So I guess, okay, we want to get rid of the v in the y dy in this part. So that's definitely part of what we're dividing. Here, we want to get rid of y squared because we have v and dv. So imagine someone that's different from the group would be segregated, no? So if a friend group shares the same interests, someone doesn't, then it's easier for that person to be left out, no? I'm just trying to cite an analogy so it's easier to understand. So y squared. Now let's simplify. We have dy over y plus v dv over v squared minus uv plus 1 equal to 0. Okay, now let's start integrating. So ln y plus, okay, how do we integrate this? Let's try u as v squared minus 2v plus 1. That's gonna be 2v minus 2 to v minus 1. You can't, no? Actually, if we want to try long division, you actually can't. What gives you the idea that you cannot do or perform long division is because the highest degree of the denominator is greater than that of the numerator. Therefore, what we do here is called partial fraction decomposition. So how do you do that? I think there is actually a reason why we could factor the one below. So v minus 1 minus 1. Yeah. So 1 over v minus 1 times v minus 1. We can write this as a over v minus 1 plus b over v minus 1. Simplify further. So we multiply both sides with this, no? So we only have 1 in the left side. At the right side, we get this. So we now have to identify the value of a and b. So there are two methods. Method 2 is more complicated. I don't really remember how to do it anymore. But method 1, it's usually applied for simpler scenarios, such as what we're looking at right now. So um, let's try v equal to 1. Obviously, because it's gonna make it 0, no? What do you think? 1 equal to a times 0 plus b. This doesn't look right though. Hmm. Let's check what the solution has to say. Ah, wait. Let's try squared here. Yeah, that's more like it. So if you want to make v equal to 1, when you substitute, so that becomes 0, b therefore is equal to 1. Okay. This is allowed, just to let you know. That's something that I just discovered now. I did know about it before, but you know, there's some things that you learned before that you tend to forget. So now I remember it, and I can confirm that that's actually allowed. So it just so happened that in this case, um, we have two that are the same. So we write it in this fashion. So one has a degree of 1, the other has a degree of 2. Okay? So what if does it still matter what A is supposed to be? We already know what B is. Let me just search. So one thing is certain, this one is gonna be 0 always, no? Because we know that B is equal to 1, the other side is equal to 1, this is supposed to be 0. There is a chance that A is 0, but how certain are we, no? I guess it boils down to doing this. 1 is equal to 0 plus B. Oh, no, no, no. A times quantity V minus 1 plus 1. So 0 is equal to A times quantity V minus 1. So yes, I think it's safe to say that A is 0. Now that we've identified A and B, Let's now substitute. A is 0, no? And B is, well, 1. Again, we are trying to derive this, no? I think it didn't help. Is it possible that um, no, I don't think that's possible. This is actually driving me crazy. Um, Perhaps, let's say A is equal to 1. Because something tells me that this is technically valid. Wait, I think I see my problem now. Yes, I think I see the problem. So I didn't account for V here. You're supposed to. Let's repeat this entire thing again. So how do we do that? Mm, now what? Let V equal to 1. 1 equal to A times 0 plus B. Okay, so B is equal to 1. That's established already. What if, let's further simplify, AV minus A plus B. Let V equal to 0. 0 is equal to 0 minus A plus B. A equal to B. So we established a connection. A is equal to 1. Is that actually possible? Okay. So copying this, substituting, we have this, okay? So don't forget the integral sign and dv. Okay, let's now integrate. It's much easier this time. So u is equal to v minus 1 du, therefore is equal to dv. So du over u, ln u being v minus 1, plus, what's this? V minus 1 raised to 2 du is equal to 2v minus 1. No, that's not possible. I think we have to perform partial fraction again. Yes, we have to. Technically, the degree of the denominator is greater than that of the numerator. So 1 over 3 minus 1 squared. It's actually what we did a while ago. Let's just rewrite it. So 1 equal to A times v minus 1 plus B. Let v equal to 1. So b is equal to 1 also, no? A is 0. So that didn't change anything though. Mm, this kind of question is actually a nightmare. My gosh. I'll get back to this question.